last speaker, we have Alex Kissinger, who will be talking about the state of the art of understanding and doing quantum error correction using ZX diagrams.
Okay. All right, that's visible.
Yep, great.
Okay, yeah. So yeah, there's not so much time, and I'm going to talk about a lot of different things here. But I did put the slides on the Discord, so if at some point things are flying by too quickly, have a look there. Okay, so I'm going to talk about quantum error correction and specifically things people have done in ZX to look at QEC. So just so we're kind of on the same page, what is quantum error correction? The idea is you encode some space of logical qubits into a bigger space of physical qubits. Okay, so normally we think about K logical qubits embedding, possibly by some isometry, E, that exists maybe only in our minds, into a bigger space of N qubits. Now this isometry E, or sometimes just the subspace of its image, is called a quantum error correcting code. And these things are used to encode, sometimes decode logical states, measure physical qubits to detect and correct errors, and do fault-tolerant computations directly on encoded qubits. So that's why I say only sometimes decode. You might think about encoding your qubits and then doing everything inside the code, and then just even doing an encoded measurement at the end. Okay, so in ZX, there's been two, I would say, main approaches. Oh, somehow I paused my screen share. Okay, there we go. Two main approaches people have looked at. So there's been other things, but these were kind of the main approaches people have taken. So one is a kind of a graphical encoder approach to study quantum error correcting codes. So there's a couple of papers with Grok in the title, like how to graphically Grok X. And the idea here is that we just take this encoder map and we draw it as a ZX diagram, and then do all of the work in terms of this graphical encoder. Another quite different approach is what's called the Pauli web approach. So this is where you actually draw some circuit of operations, which could be unitaries or projectors, and you kind of reason about what's happening with the errors inside of that circuit using ZX techniques. Okay, so let me start with this encoder approach. I'll talk the most about it because that's mainly what I've worked in. So the idea is to represent the encoder as a isometry directly as a ZX diagram. And the idea here is that different fragments of ZX correspond to different kinds of quantum error correcting codes. So the most common kinds are, if you focus on the Clifford fragment, you get stabilizer codes. If you focus on the phase-free fragment, you get CSS codes. And then we can think about fault-tolerant quantum computation using this technique, which we sometimes call pushing through the encoder. So you think about something happening on the logical side here, and you can push it through this encoder to see what its equivalent is on the physical side, or pull it back to do vice versa. Okay, so I'll just say very quickly what a stabilizer code is. So these are codes whose subspace is fixed as the +1 eigenspace of some commutative subgroup of the Paulis. Okay, so we take something called a stabilizer subgroup, and we just look at all the states, which are +1 eigenvalues of that group, and that defines a subspace of K qubits inside of our big space of N qubits that this n-fold Pauli group is over. So E is fixed by the stabilizer generators, so we can describe this thing efficiently. And if we think about, well, so E is not quite fixed by these. It's fixed by the stabilizer generators and also 2K more logical operators. So the stabilizers are the things which are invariant on E. So if I do it in the range of E, nothing happens. The logical operators are the things that sort of push through E. So if I take a Pauli X on the ith qubit, it pushes through to the ith X logical operator, similar for Z. And then this is enough data to fully reconstruct this map. So we detect and correct errors by measuring the stabilizer generators. And the code distance is the way to the smallest undetectable error, which tells us how many errors we can detect and correct with this code. CSS codes are a bit simpler because we just take a stabilizer code and we split it into two halves. One half has only support in X and identity Pauli operators, and the other one has only support in Z and identity Paulis. And these are quite convenient to work with because it's equivalent to having a pair of orthogonal subspaces of the two-element field, so orthogonality captures the fact that these things need a commute, and these things act like subspaces to capture the Pauli multiplication. Right, so the reason these are easier is because we can import stuff from linear algebra, classical error correction, or use phase-free ZX diagrams to talk about them. Okay, so this is the phase-free fragment. It's built out of these zero-phase spiders. And the thing that these have to do with F2 linear algebra is actually, I can think of this as a copy map, and I can think of this red dot as an XOR, or an addition modulo 2. So that's addition in my finite field of two elements. So as it was already mentioned, these things have a nice normal form. So I can always efficiently reduce a phase-free diagram to something that looks like this. You'll notice throughout this talk, I'll link to the place you can find it in Picturing Quantum Software. So indeed, you can see this in detail there. And in the special case of isometries, you can actually show that this J part, so these are the isolated red dots, will always disappear. Okay, and that has to do with the fact that an isometry is injective, and this kind of measures non-injectivity of the map. Okay, so I get this nice, slightly reduced normal form. And something that's quite cute about this is I can read the stabilizer info directly off of such a normal form. So first of all, this isometry is described this way. And if you know about these kinds of things, this looks like the definition of the code words of a CSS code. But to put it a bit more in a bit more basic terms, I can write the adjacency matrix here as L, so the thing connected to the inputs, and the thing not connected to the inputs is S. The columns of L tell me my logical X operators. The columns of S tell me my stabilizers. Okay, so in general, I could have lots of columns here, and that would give me the stabilizers of my code. Okay, so I can read that straight off the diagram, which is quite convenient. And since everything is color dual in ZX, I can also do this. I can get an equivalent picture of the encoder, which tells me my Z logicals and Z stabilizers. Okay, and a nice thing about CSS codes is I only really need to know just the X part or the Z part, because the other kind is uniquely fixed. Okay. Another thing that's quite handy with these things is to use scalable notation. So this little arrow really just means this. It means just put that by adjacency matrix in that spot. Okay, so I can write this very succinctly using scalable notation, and that's quite useful for working with CSS codes. So one of the ways it's useful is you can think about transversal Clifford gates. So these are gates which act only on single qubits in each code block. And for instance, this is the proof that doing a C0 transversely on a CSS code physically is the same thing as doing a logical transversal C0. Okay, and you can see it's a pretty compact, nice proof using the scalable notation. You can also use this kind of notation to talk about transversal non-Clifford gates. The only difference here is this equation here is hiding a spider nest identity. So you might not recognize it in this kind of shape, but if you know about these things, this is in fact a spider nest identity coming from the fact that you have what's called a tri-orthogonal code, which are the kinds of codes that have transversal T-gates. Okay, and yeah, finally, one more thing that's been done in the encoder approach with CSS codes is to talk about lattice surgery. Okay, so this came up, this paper of de Beaudrap and Horstman came up with this logical level picture of lattice surgery operations. So this here is a picture of a logical merge, and what you see here is a proof of how to implement that at the physical level. So I can take two patches of the surface code, which look like this. I can do measurements along the boundary, and I can push it through the encoder to get a logical merge. These things have been used to think about code transformations. So this kind of transformation is called code morphing. This is called gauge fixing and subsystem codes. But I'm just kind of going to say these words and point to this archive link for what those mean. So that's kind of what I wanted to say about CSS encoders. There has been some work in stabilizer encoders as well, though they're not quite as well understood, in that there's more choices to make when you pass to stabilizer theory, to the full power of stabilizer codes. Okay, so generic stabilizer codes correspond to the encoder, which is any Clifford ZX diagram. Okay, so now the phases are integer multiples of pi by 2 rather than just 0. Clifford ZX diagrams have multiple efficient normal forms, and some are useful for some things, some are useful for other things. So for instance, there's this GSLC form, graph states with local Cliffords, inspired by measurement-based quantum computing. There's also what we call in the book the AP form, so where you have a kind of an affine subspace part, which you can kind of think of as your CSS code part, and also a phase polynomial, which is a diagonal Clifford part. Okay, and you can relate these two things in various ways. So a couple of things that have been done with stabilizer encoders. So for one thing is using a variation on the GSLC form, you can actually give canonical forms for encoders. So you can give a unique form of your encoder, which allows you to really canonically express a code. And also it helps you with various kinds of things, like if you want to combinatorially explore the space of codes, then you can start to enumerate, say, equivalence classes of codes using these canonical forms. And one more application was looking at concatenated graph codes. So these are a type of stabilizer code based on graph states. And one thing that you can do that's quite nice is if I take a graph code and I encode each of the qubits in it in another graph code, then just doing a bunch of pivots, I can see that this thing is itself a graph code. It's just with a more complicated connectivity. Okay, so that's kind of what I wanted to say about the encoder approach. In the last couple of minutes, I just want to talk very briefly about Pauli webs. So the motto of this kind of approach that I've heard a couple of times now is that you want to think about circuits and not codes. So the idea is to think about a possibly infinite or periodic sequence of gates and measurements as a generalized quantum error correcting code. Okay, so it's no longer just measuring the stabilizers of a stabilizer code over and over again, but just more general stuff. And now the physical qubits are still the wires passing through here, like in a normal circuit. But the logical qubits are kind of hiding inside. And the way you can reason about these and also the error correcting properties is defining certain kinds of colorings of this thing called Pauli webs. So the Pauli webs really measure how Paulis will propagate through these diagrams if they're introduced in certain places. And they can be used to study, well, normal stabilizer codes, just using the circuit which measures the stabilizers. Floquet codes, which are based on measurement schedules. So it's like a periodic sequence of measurements that can be non-commutative. So here the code space is changing all the time. And you could also have more general codes where we just kind of do stuff and we see what kinds of properties this has. So you can define general notions of code distance, start to reason about that. So an application of this is you can really think about lots of different kinds of fault-tolerant protocols as just different readings of the same ZX diagram. So there's this paper on unifying fault tolerance. And you can also think about Floquetifying stabilizer code. So I can take, say, a stabilizer measurement circuit, I can do some unfusions, and I have a Floquet code. Okay, so this is from one of Teague's papers, and this has actually been Rodetz's picture, so credits to him. Yeah, so that's kind of what I wanted to say about Pauli webs. There's lots of other stuff in this area, so I just pulled a few recent things. So thinking about QDIT odd prime qubit stabilizers, you can actually use something called graphical symplectic algebra to reason about these things. Annoyingly, it doesn't work for qubits for technical reasons, but this gives a calculus for that. There's some trichromatic variations of ZX for looking at different kinds of codes, and more exotic topological things like these genome codes. Okay, and you can see now there's probably something like 20 or so papers really about error correcting codes in ZX on the ZX website, which are all worth a look. So I think that's where I'm going to stop. So happy to take a couple of questions if there's any time left.
All right, great. Thanks, Alex. Yeah, before we go to questions, I just want to point out that